This is section 8.5, the last section of chapter 8, the dot product. It's the general term of it. So this starts off with the dot product. The dot product looks like this, where it looks like u and v are multiplying, which we do multiply in parts of it. You multiply the fronts, and then you multiply the backs, and you add them together. That is a dot product. The dot product is not a vector. It's a scalar. It's like an actual numerical value that we use to find other things. So the actual just plain dot product alone has no meaning, but we use it in other formulas in a little bit. So if we want to find the dot product of A and B, we're going to do 3 times 1 plus negative 5 times 4. Multiply the fronts together, multiply the backs together, and we add them. And we get 17, negative 17 here. For this one, we do the dot product for A times B. 6 times negative 1 plus 2 times negative 2. And here we get negative 10. Properties of dot products, the same properties that we have all the time. We have commutative, associative, distributive, and then squaring. Here is one reason where we use the dot product. This theorem, it says if theta is an angle between, I'll put these both up at the same time, and we have this. This is really, we use this formula way more. So this one right here is one that we use more. Something on the final exam we will have vectors on, which I know I didn't say it in the last section, but somewhere on your final exam you will have vectors, whether it be finding an angle between them, finding the magnitude, finding the actual vector from a terminal and initial point. Something on vectors will be on your final exam. So we're going to use this formula here, the angle between two vectors. If we are given this vector of 7, 5 and vector 40, negative 9. So the formula, start with cosine theta. On top of the fraction is actually the dot product of the two vectors. So 7 times 40 plus pi times negative 9. On the bottom is the magnitude of each vector and then multiplied together. So 7 squared plus 5 squared multiplied by 40 squared plus negative 9 squared. All right, you punch that whole thing in the calculator. Do second cosine. Theta ends up being 48.2. So between these two vectors, there's a 48.2 angle. Vectors are not called perpendicular. Two vectors, two non-zero vectors are called perpendicular. They're not really called perpendicular. They're called orthogonal. This fancy word of orthogonal. Because the angle between them is 90 degrees. And this is easy to find out. If their dot product is 0, then they are perpendicular. So if we need to figure out whether they are orthogonal or not, I just have to do their dot product. Well, this equals 0. So yes, they are orthogonal. Oh, oops, I don't want that arrowhead there. 3 times negative 3 plus 4 times 4. This is not going to equal 0. This is 7. So this would be a no. My phone's ringing. Oh, that's... Okay. And moving on. So the second one is not orthogonal or perpendicular. Let me get this down. Now we have a component form of vectors. I'm not really 100% worried if you fully grasp this, because I'm not that worried about it. But we will touch on it. So there's some pictures of what they look like. And then we have this question about a car. A car is weighing 3,000 pounds. It's parked on a driveway that's inclined 15 degrees to the horizontal. And there's all the pieces that you need to know. We want to find the magnitude of the force required to prevent the car from rolling down the driveway. Well, the car is 3,000 pounds, and the angle where the car is to go backwards down the driveway is 75. So the magnitude of it, 3,000 times cosine 75. If you look up above, they're using u cosine theta. This comes out to be 776. These are rounded. That's for part A. And then they want to find the magnitude of the force experienced by the driveway due to the weight of the car. Well, the actual incline is 15. Okay, see that where this is 15 right here? So here, the magnitude of u, 3,000 cosine 15, ends up being 2,898. Calculating components. It's this piece. These questions will specifically say, find the component of u along v. If it says that, you use that formula. So we're going to do the dot product on top. 3 times 4 plus 2 times negative 8. And then do the magnitude of just v on the bottom. So the square root of 4 squared plus negative 8 squared. This comes out to be negative 4 over 4 square root 5. Our 4's can reduce. Rationalize the denominator. Negative square root 5 over 5. Calculating projections of u onto v, which is different than doing a component of u along v. But it has to do with part of it. Like there's a piece in there that has to do with it. So if we want to find the projection of v onto u, which is this fancy symbol right here, that's how it's written. We're going to use that formula. So we got to do the parentheses first. So this is for part A. On top of the fraction, you do the dot product. On the bottom is just the magnitude of v. The only difference in what we just did in the previous example is that we're actually going to take this and square it now. And then we're timesing it by a vector. So this whole parentheses in the beginning ends up being something. Oh, what does it come out to be? 4 squared plus, so 16 and 64. Since the square root and squared cancel. I feel like 16 and 64. All right, this set of parentheses ends up being negative 4 on top. Oh, this is, say 80. That does say 80. That can't be right. Is that right? Yeah, that's right. Just kidding. That's right. Yep. Please be patient with me. Some of these videos, for sure. So that negative 4 over 80 is actually a scalar. It's like one number. So we're going to distribute that in. That's really, so this ends up being negative 16/80ths and positive 32/80ths, which both can be reduced. So that's negative 1/5 and 2/5. And then it says resolve u onto u1 and u2, where u1 is parallel to v and u2 is orthogonal to v. That's a whole lot of words. All right, well, u1 is just what we just did. This is u1. So for part B, that is u1. Because if you look up at the box above, it says u1 is the projection of v onto u. Pretend that you can read that. And then u2 is u minus the projection. So if we have our original of u, we're going to subtract these two, this u minus u1. So u2 ends up being 16/5, 8/5. All right. Bottom, there is one piece that's missing. We have this work equals force times D. Well, to find F, the force part, you do the magnitude of the force times cosine theta. You gotta write that in. That part we're missing. So calculating work. So if we have a force that's given by the vector 7, 6, moving along the object 2, 1 to 0.56, find the work done. Well, we need to find the actual distance, like D, right? Using this as an initial terminal. So 5 minus 2, 6 minus 1. This vector is 3, 5. So to find work, force times D, so we're doing the dot product. So 7 times 3 plus 6 times 5, the work done is 51. Another calculating work one. A man pulls a wagon horizontally by exerting a force of 30 pounds on the handle. Handle makes a 70 with the horizontal. Find the work done moving a 200 foot. Moving the wagon 200 feet. All right. So we're going that way. We're moving it 200 feet. So this is going to 200, 0. This is 70 degrees. So to find the distance is 200, 0, because it's not going up or down, just to the right. Our force is 30, oh, let me get that in there. Oh, I'll just rewrite it. Force 30 cosine 70 and 30 sine 70. These are some decimals. So to find work, force times D. So we get 200 times 30 cosine 70 plus 0 times 30 sine 70. So the back part's definitely 0. The front part is 2,552.1. And that is our entire chapter